Okay, let's talk about the middle solar system, basically the region between Jupiter and Neptune, 5 to 30 astronomical units. The idea is that this region contains a lot of objects that may have rained out from the Kuiper belt. So, there are many things I could say about this. There's a lot of work done on objects in the middle solar system. Everything is easier in the middle solar system observationally because it's closer and brighter, it's easier to study. So we have a lot of data. I just want to pick out three things to talk about. First of all, color systematics as a tool to try to understand what's happening. I'd like to talk about amorphous ice because one of my favorite subjects, and I think amorphous ice potentially is very important. And then I'll talk briefly about the Trojans of the planets. And I hope not to take too long with this, so I'll go fast. So, you can imagine the protoplanetary disk accreting into solid objects. Products of the accretion of the protoplanetary disk are the Kuiper belt that we talked about a little bit, the Oort cloud that we talked about a little bit, and there's something we're going to talk about, the main belt comets, the active asteroids, coming up in the inner solar system. So forget those for now. These three reservoirs of comets are basically capable of feeding other populations. So the Kuiper belt loses objects when they move into the region of the giant planets. We relabel them Centaurs. When they come inside Jupiter, they're Jupiter family comets. And then when they run out of gas, they're dead Jupiter family comets. And they end up by hitting a planet or the sun, or being ejected from the solar system maybe, or just falling to bits. They disintegrate. And there's another pathway from the Oort cloud down through various flavors of things in the solar system towards eventual destruction at the bottom. Okay, so just imagine this rain of particles coming down from the outer solar system towards the sun. We're studying that rain in essence. So the Kuiper belt rains debris into the planetary region of the solar system. Objects around the giant planets are called the Centaurs, and Centaurs become Jupiter family comets. So we know that's happening. We kind of see that happening in all sorts of ways. In the past, when the Kuiper belt was more massive, presumably it was a much more massive source of particles of rain for the inner solar system. And there is a suspicion that the Kuiper belt could have supplied some of the populations which are weakly trapped. So notably the Trojan asteroids, the irregular satellites, and maybe a few other populations in the solar system had their origins in the Kuiper belt. It's possible, not yet really established. So let's start by talking about color systematics of bodies coming in from the Kuiper belt through the Centaur phase into the comets. Now, what is this color? Why are we talking about color? Well, we'd like to talk about composition, but in general, we can't measure composition because we can't do sample return from these objects. They're just too far away. So the next best to sample return is spectral composition. Well, we can't do spectral analysis of most of these objects because they're far too faint. So color is kind of a proxy for a spectrum. Color is like a poor man's spectrum, a very poor man's very poor spectrum. And we use it as a measure of composition, but it's not diagnostic. So we can't say that we measure this color and it means this composition. But we can use it as kind of a tool to compare populations. Things of the same color, may be related, things of different color, maybe not. So we use it in this very basic way. And I'm going to refer to for the most part to color in the astronomical sense, which is the difference between two magnitudes, BV, VR, which is really the ratio of flux densities of two wavelengths expressed as a logarithm and multiplied by 2.5 in the way that astronomers do that. But also you see color mentioned as a spectral gradient. It's a linear slope of a spectrum plotted against wavelength. So here's a summary diagram. So this is a plot that shows two different color indices, BV and VR. And the important thing to know is that things towards the upper right are redder than things towards the lower left. That yellow dot is the sun. That's the color of the sun, about 0.64 and about 0.36. And then all of the other objects on there are small body populations in the solar system, okay? That black line is the locus of points that have basically a straight spectrum. The gradient is constant with respect to wavelength. And if you're above or below the line, then the spectrum is curved, this way or this way. It's positive curvature or negative curvature, but looks like most of the objects have a pretty straight line reflectivity spectrum. Now, what the plot shows is that all the really red things up there in the upper right are parts of the Kuiper belt. They're components of the Kuiper belt. The reddest objects are in the cold classical Kuiper belt, the cold CKBOs at the top right. And they and some other populations are coated in this material that I call ultra-red material. It means the practice B minus R is bigger than 1.6. The gradient is bigger than 25% per 1,000 angstroms. So this ultra-red material is fairly abundant in the Kuiper belt, but it's not seen in these other populations. So if you look down towards the lower left, Trojans don't have it. They're just not that red. The active Jupiter family comets, the Centaurs, the Damocloids, Jupiter family nuclei, and so on, don't have this ultra-red color. And yet, if they're all related, if many of these bodies are just the rain coming out of the Kuiper belt, why don't they have the same color? So we just look at that and talk about that a little bit. The circles with letters inside are the colors of asteroids. So here's similar data, BV versus VR for 4 different populations. So in the top left are just the long period comets. These are bodies from the Oort cloud. And what you see in red is that they cluster around small values of the color. They're redder than sunlight, but small values of color. In the background are the colors of Kuiper belt objects, which extend over a huge range from nearly solar color at the bottom left to ultra red at the top right. And you can see the comets don't share that range. Okay, fine. The Damocloids, what are they? They're the nuclei of long period comets. So the coma is gone, so we're not confused by scattering colors from dust. And again, you see the colors are clustered down on the blue end and not in the red end. There's nothing up there at the red end. Let's look at the Centaurs. So these are bodies interacting with the giant planets dynamically. Again, there's a bit of scatter and there are not many measurements here, but there are no cases of ultra-red active Centaurs. These are ones with outgassing material. And then if you look down in the bottom right, the only case where you see this ultra-red material in a population other than the Kuiper belt objects is in the inactive Centaurs. So we've got bodies which are dynamically equivalent, the active Centaurs and the inactive Centaurs, but they have different color distributions. And the color distribution of the active Centaurs is like the regular comets and the Damocloids, and it's not the same as we see in the inactive Centaurs. So there's the same figure just shown large, so you can resolve the points a little bit better. The point is that, these Centaurs are all the way from blue, basically just slightly redder than sunlight, up to ultra red at the top right. And in fact, you can get a sense that they're probably bimodally distributed. They're clumped in the blue and they're clumped in the red. So what do the active Centaurs look like? Well, there they are. There's some. They look like comets, because that's what they are, right? They're active at distances which are too large for the activity to be caused by the sublimation of water ice. They're too cold for that. But there's some other process, some other volatile, maybe CO or CO2, that's expelling material from these bodies. These are typically, 10 kilometer sized Centaurs that we're seeing in the inner parts of the Centaur region. They're active bodies because they're actively sublimating in the heat of the sun. Okay, so that's what they look like. Here's the distribution of Centaurs as a function on the left of semi-major axis and on the right of perihelion distance, plotted against eccentricity on the left and inclination on the right. So look at the left first of all. There's a whole bunch of different objects plotted there. So we have the Kuiper belt objects shown in orange are the classical and the resonant Kuiper belt objects. So they're a bit beyond Neptune and the eccentricities go up to 0.4. The yellow circles are Centaurs and scattered Kuiper belt objects. And as I mentioned before, they're dynamically more or less equivalent bodies being scattered by the giant planets. And then the red dots, forget the blue ones for now, but the red dots are active Centaurs. And so meaning that they look like comets. And so what you might notice is the red diamonds are concentrated over on the left-hand side of that plot, which means they're concentrated towards small perihelia. So that's more explicit on the right-hand side. When I've plotted the perihelion distance, you can see all the red diamonds are over there on the left, inside about 10 AU. So we don't see any active Centaurs beyond about the orbit of Saturn, something like that. Okay, so that's an observational fact. Now, when you plot color of objects against their perihelion distance, perihelion because they reach the highest temperature at perihelion, and so they're most likely to be active at perihelion. What you see is kind of a transition that happens around this distance of 10 AU. So beyond 10 AU, we see the red Centaurs up at the top, and we see the not red ones down at the bottom, the blue ones. I've actually made them blue in this plot. And I've plotted the active Centaurs with big yellow circles, so you can distinguish those. And it all changes when you go inside 10 AU, certainly when you're inside 8 or 7 AU, it all changes, and the objects become devoid of the ultra-red population. So what we see is kind of a transition from bimodal colors at large perihelion distances to unimodal colors at small perihelion distances, consistent with the idea that this ultra-red material, which is present in the Kuiper belt and in the inactive Centaurs, is somehow destroyed when it comes inside about 10 AU. So let's just talk about that. So there's some kind of evolutionary process going on as material comes in. Now, we don't know what that is, just as we don't know what the ultra-red material is. We have ideas, but we don't know. We suspect the ultra-red material is organic. We suspect that because the material surfaces are relatively low albedo and spectrally bland. So, you know, if you take a spectrum of a piece of toast or something, you don't see absorption bands in the toast because all the bonds have been destroyed by the cooking, by the high temperature caused by the radiation inside the toaster. So it is with material on these objects. The chemical bonds in the surface are probably largely broken up and destroyed by cosmic ray bombardment over long periods of time. But there are materials that do show color. And so this is a recent paper by Sakakibara from 2020, showing a material which at 85 Kelvin or 100 Kelvin or 120 Kelvin is red, certainly red enough to supply the colors that we need, but loses the redness as the temperature goes over about 130 Kelvin. Okay, so this is the kind of thing that might explain the loss of color. You have a thermodynamically unstable material. These all contain nitrogen, so these are nitrogen-related colors. This material just cannot survive. But you have the idea that there's probably this material in the outer solar system that just doesn't make it in towards the sun. Okay, so that's one idea. Another idea is that it's the activity itself that destroys the ultra-red material. And the mechanism there would be ballistic resurfacing. So when a comet loses material, blows out particles, the particles come out with a velocity distribution. And so the bigger particles come out more slowly, and they're more liable to fall back onto the surface. And so they basically can coat the surface even as smaller, faster particles go out faster than the local escape velocity and make it their way into the coma. So ballistic resurfacing, if you try to calculate how quickly that can happen, turns out to be really, really fast. Okay, so I have a little plot showing ballistic resurfacing times for objects of a given size and a given mass loss rate. And you can see the numbers on the curves. They're measured in years, not millions of years, but just years for objects with radii that we care about, like 10 kilometers, something like that. So ballistic resurfacing, I think, potentially is capable of transforming these bodies from ultra-red to neutral by burying them in debris, by excavating material brought up from below and dumping it on the surface. So the model is that the surface is ultra-red because the organics on the surface have been cooked, they've been processed by cosmic ray bombardment over a long period of time, probably hundreds of millions or billions of years. that chemical ray processing extends to depths of probably a meter or a few meters. And if you can dig up material from beneath that and then dump it on the surface, you would hide the ultra-red material, okay? So we see, some evidence in the color data that, sure, there's a connection between the Centaurs and the Kuiper Belt objects, because indeed, only the Centaur population has this ultra-red material. Nothing else in the solar system does, although it's abundant in the Kuiper Belt. But as you come closer to the sun, it gets destroyed somehow. Now, there's another mechanism that might destroy it, and in fact might work by providing the activity that we see at distances where temperatures are too low for water ice to sublimate, and that's the crystallization of amorphous ice. So I love this subject. I'll talk about this, and we'll see where it goes. So you know that the ice in your fridge is crystalline. So it's sitting in a hexagonal, close-packed arrangement. All these molecules are hydrogen bonded together. But you probably also know that if you accrete ice at very low temperatures, if you have a cold plate and you put down molecules one by one, if the temperature is very low, they don't have enough kinetic energy to bounce into any kind of a crystalline organization. They just kind of freeze where they stick. So that's amorphous ice. It's a big jumble of molecules with no particular geometrical arrangement between the molecules. Now, amorphous ice is always, at every temperature, thermodynamically unstable. And it always tries to transform to the crystalline energy state, because that's a lower energy state. And if it can make it, it's going to release that energy. It's about 100,000 joules per kilogram. It's quite a lot of energy. So the transformation from amorphous to crystalline is exothermic, okay? It's a good source of energy. So that's interesting from the point of view of people who study comets, for example, who need energy at distances beyond Jupiter where there's not enough energy to provide the sublimation of water ice. The timescale for this transformation is a ridiculously strong function of temperature. Okay, so there's the function at the bottom. It's that exponential. EA is an activation energy for the transition from amorphous to crystalline. But basically, at temperatures you find in your refrigerator, the crystallization time is like 10 to the minus 12 seconds or something. So you always have crystalline ice, not amorphous ice, in your fridge. At least I hope so. Whereas at temperatures below 77 Kelvin, the crystallization time is equal to or longer than the age of the solar system, okay? So let's have this little video. It's an amusing video of symbolizing crystallization. So it's a gentleman with a large number of mousetraps and a great deal of bravery. I'll just let this video play. And so you can see, he supplied a little bit of energy with his hands coming down onto the mousetraps. But that little bit of energy has released energy previously stored in the mousetraps by whoever put the springs back. And they all start to jump up in the air, and then the whole lot goes. It's kind of a runaway explosion, a bit like a nuclear reaction, no nuclear involved. So that's the idea of a crystallization runaway, that if you can crystallize a little bit of amorphous ice, the energy that it releases by virtue of being exothermic can perhaps heat the ice next door and take it up into a regime where it can quickly crystallize as well. And then it will release energy, and then that will warm the ice next door, and then that will crystallize. And so you have this runaway of crystallization going through a body. So this idea is actually pervasive in people who study the thermal evolution of comets. The idea is the comet is full of amorphous ice, and it crystallizes when the comet gets hot, and there can be a crystallization runaway. Now there's this plot of the crystallization time. Once I've repeated the equation at the top, the crystallization time as a function of temperature. And the point is that all of the Kuiper belt is below 77 Kelvin. That means that all of the ice in the Kuiper belt, in principle, can exist in the amorphous state forever, for the age of the solar system, okay? But as you come into Uranus, that timescale shrinks to 1 million. As you come into Saturn or something, it's down to about a year, roughly, and Jupiter about a second. So the crystallization becomes incredibly rapid when you come in close to the sun. Okay, so that's the idea. Maybe the ice in the Kuiper belt is amorphous, at least in part. And maybe when it comes in, it's responsible for the crystallization and then an explosion of activity that causes the active Centaurs and causes the destruction of the ultra-red matter by burying it on the surface. Here's a plot that just compares the Kepler time, the orbit period, with this crystallization time for two different simple thermal models of the surface, basically the hottest possible one and the coldest possible one. And the equivalence of these times occurs at points A and B. It basically says crystallization must happen somewhere between 6 or 7 AU and about 12 or 13 AU at the outer edge. So that's an order of magnitude estimate. The calculation has been done in detail by Aurélie Gilbert-Lepoutre, who has studied the stability of amorphous ice on the surface of a rotating body as a function of distance from the sun and obliquity. And so this plot just summarizes the results. The dark blue stuff is mostly crystalline, the white stuff is mostly amorphous, and it confirms the result that you get from an order of magnitude calculation that the critical distance is about 10 AU, but it's somewhat orbit and obliquity dependent. And then that thing at the bottom just reminds you that this crystallization is stepwise. So crystallization will propagate down, but when it propagates into ice that's too cold to be raised up to the effective crystallization temperature, then the crystallization front will stop. So if you look at that black line on this model of a Centaur, the crystallization goes down to a certain depth, and then it stops and it waits for the next pulse of heat to come from the next perihelion, and then it goes down again. And then it waits for the next pulse of heat from the next perihelion. So you have these steps of crystallization going down into a body. So all of that's pretty cool, I think. It's consistent with this distribution of active Centaurs. The activity is confined to distances less than 10 AU because that's where crystallization occurs. Now, a side benefit of this idea is that amorphous ice is a very good sponge for other gases. So you can pack a lot of other gases in the nooks and crannies between the molecules in amorphous ice. And then when you crystallize that ice, all those nooks and crannies close up and the trapped gas is squeezed out. So this has been simulated in the lab by Akiva Bar-Nun and other people. And basically the result is, yes, you can trap a lot of gas in amorphous ice. So it gives rise to the idea that maybe the Kuiper belt objects are, gas bags. They're frozen gas bags that release a lot of that gas when they crystallize as they come in towards the hot sun. And maybe crystallization runaway is important. Now, is there any direct evidence for that? No, it's circumstantial. Here is a comet which exploded. This is this famous explosion of 17P Holmes a few years ago, 10 years ago, showing a dramatic burst of activity that is consistent with heat propagating down into amorphous ice and causing a gas release and an explosion. So we see events like that in comets. They're probably much more common than we think they are, and they're totally consistent with the presence of amorphous ice. But the puzzle then is, if the ice in comets is amorphous and the comets just came in from the Kuiper belt, then the ice in the Kuiper belt must be amorphous too. Is that the case? And if it's the case, how is that possible? Well, in the bigger Kuiper belt objects, it probably is not possible because the big guys self-heat by the binding energy, the gravitational binding energy, and by release of radioactive decay energy in these bodies. So the big ones are probably too hot, except perhaps for a surface shell of amorphous ice around the outside. Smaller ones may be indeed amorphous on the inside. And this would be consistent with low temperature formation and consistent with the trapping of large amounts of gases like carbon monoxide that we do see leaking out of comets when they come close to the sun. Okay, let's talk about the Trojans and a thing that I'm calling the Trojan color conundrum. So it's been noticed that when you clear out the Kuiper belt, you start with this 20 or 30 Earth mass Kuiper belt and you clear out the material, a lot of that stuff is going to come in towards the sun. And maybe it could be grabbed in various dynamical niches elsewhere in the solar system, in the places that people talk about, usually are the irregular satellites of the planets, the Trojans, maybe parts of the outer asteroid belt, and so on. So that picture is just kind of a stock picture of Phoebe. It's a 200-kilometer sized Saturn satellite that might once have been a Kuiper belt object. So the Trojan issue here is that if the Trojans were captured from the hot population of the Kuiper belt, not from the cold population, because that we think is stable, it's low velocity dispersion. We think cold classical Kuiper belt has kind of always been like that. But from the dynamically excited part of the Kuiper belt, then you might expect that the Trojans would look like the hot population of the Kuiper belt. So the question is, do they? Now, we've known for a long time that actually they don't. So the Trojans of Jupiter do not have the ultra-red material that we see in the Kuiper belt. Okay, so we've known that since the Kuiper belt was first measured. Why not? So I suppose many other people supposed that there must be some kind of color evolution, like the color evolution that we see in the Centaurs. So they come inside 10 AU, something happens, maybe it's crystallization, maybe it's some thermodynamically unstable molecule, but the color transforms and the ultra-red stuff goes away and you're left with everything being the same kind of a bland, slightly red, mostly gray color that many, many objects have in the solar system. That's possible in the case of the Jupiter Trojans, because the Jupiter Trojans are quite hot. You know, their temperature is 100, 120 Kelvin or something like that. It's easily enough to trigger crystallization of amorphous ice, if that's the process. And it's also enough for the color transformation that we showed in the lab earlier. But what about the Trojans of Neptune? So the Trojans of Neptune basically are at the same place as the Kuiper belt. They're at 30 AU, you know, and the source region is just beyond that, 35, 40 AU maybe. So the temperature, which depends on the inverse square root of the distance, doesn't really differ between the Neptunian Trojans and the Kuiper belt. So you can't really appeal to any thermal process to modify the colors. So, you know, I measured the colors. Here we've got the colors of the Jupiter Trojans in blue down at the bottom. And there's the color of the Neptunian Trojans in blue down there at the bottom. And lo and behold, the Neptunian Trojans are just like the Jupiter Trojans. And neither of them is like the supposed source population in the Kuiper belt, the hot population of the Kuiper belt. So that's the conundrum. The conundrum is that, yeah, maybe you can explain the blue colors of the Jupiter Trojans by some thermal process, but no, that doesn't work for the Neptune Trojans because they're not hot. They're the same temperature as the other things in the Kuiper belt. So I showed that in a different way. Here's in the form of histograms at the top, the Neptune Trojans and the Jupiter Trojans. You can see they're basically heavily biased over there to the left, whereas the Centaurs, the scattered objects, the Plutinos, and the hot classicals, those are all hot populations, have some of these ultra-red things over there on the right-hand side of the diagram. And the cold classicals, which are not a plausible source for anything, are different, even more so. They basically have mostly this ultra-red stuff over there on the right-hand side of the diagram. So the chance, talking about statistics, the chance that you could derive these blue populations at the top from the hot populations towards the bottom is small. It's 0.4%. So this is a 3 or 3 point something sigma significant result. It's a real difference. And it's a conundrum because we don't really have a good answer for what's going on. So it's possible that more data will just resolve the difference. Maybe, you know, it's bad luck. As you know, some 3 sigma results just go away. Maybe it's bad luck. We'll get more data and we'll find, yeah, there's a whole bunch of ultra-red Neptune Trojans. That's entirely possible. Maybe there's some non-thermal evolutionary process that might happen to the Trojans of Neptune. So collisions are one possibility. You know, collisions don't depend on the local temperature. Trouble is the collision rate seems to be not enough. And in addition, the collision rate on the Trojans may not be very different from the collision rate on the Kuiper belt objects, just a little bit further out. So that's, and in both cases, the collision rates are probably too small to make any difference. So that could be true, but I doubt that one too. It could be that the Trojans are actually not captured Kuiper belt objects. So of course, this is just a model. And if it works in a model, it doesn't mean it happened in reality. There are lots of things that are done to make the models work right. You know, there's lots of cloning and stuff going on in numerical models. Maybe that's just not the way the Trojans were captured. Maybe they grew locally and were captured locally. Maybe something else is possible. I don't know. So irregular satellites, I think in the interest of time, I'm just going to skip over. It's written down. There are papers. I'm going to go on and talk about inner solar system very soon. See you in a while.